Hello, these are Flip Notes 1.5, Part 7, the last in our unit 1.5, and in this one we're learning about monocular and binocular cues, which help us to see depth.
So my Bitmoji is getting her photograph taken here, and we're able to see depth in photos through monocular and binocular cues. So let's dig into that. So depth perception is just our ability to recognize distance, whether we're in our car and we're trying to judge how far another approaching car is, or whether we're looking at an image like the one here and trying to judge how far away objects are from each other. To get depth perception, we use both binocular and monocular cues. That means two eyes or one eye at a time, and some other things called retinal disparity and convergence, which we'll get to later in this section as well. So monocular cues are things we can use to detect depth that only require the use of one eye, and it's usually to detect depth in an image. So for example, in this drawing, we know that an elephant is much bigger than a person. So why does the elephant appear so small? And we know it's because it's far away in the image there based on our experience. But our ability to kind of determine the location and the size of these objects based on each other has to do with monocular depth cues. And there are 6 of them, and I'm not going to read them all right here because we're going to talk about each one individually. So the first one is linear perspective. We're able to detect distance in an image like this because the parent lines that we know to be parallel in real life appear to be converging in the distance. So that helps us to detect depth, how far away something is. So we know that on a road, the lines are parallel, but in this image, they look like they are coming together, that they are zooming in. I'm trying to point it, you can't see. But that's linear perspective. A lot of this is going to feel like an art class because these are definitely techniques that artists would also use to show depth in their drawings. Texture gradient is the idea that closer objects are going to show more texture. And this probably isn't a great image for that, but this hay bale, we'd be able to see a lot more details up close, and things that are far away are just going to appear to be kind of as a blur. Here in an actual photo, that's my husband and I when we went to Italy for Christmas several years ago before we even had my daughter. But we appear much more clear. You can see the detailing on my coat, but in the distance, you see less details of the buildings and of the hillside, and it actually was kind of foggy back there. But because of the depth and the distance, you also don't see as many details back there. That's texture gradient. Interposition says that we can tell which objects are nearer because they're not masked by other objects. So we know that this pyramid is closer than this yellow box because we can see more of the pyramid. We know that this blue rectangular prism is closer than this red one or cylinder. I'm not sure what shape that is. The red is not masked, or sorry, the red is masked. The blue is masking the red. In this image, we're in what's that city called? Venice, on a gondola. It was freezing that day, but we are closer than the gondolier because you can see more of us. You can't see all of the gondolier's legs. We're closer than the buildings because my head is masking the buildings. That's interposition. Relative size says that objects that are closer are going to appear larger. So this was on Christmas Day, and that's the Leaning Tower of Pisa. You may not know this, but it is much taller than me in real life. And this is just something people do whenever they go there, is they take all these silly pictures. But the reason that I appear to be this size is because I am much closer to the camera than the tower is. So relative size, this is a bit of an illusion here, but I appear to be larger than the tower because of my relative size and location close to the camera. So those were all monocular cues. These are binocular cues, things that you can do to detect depth using both of your eyes. The first is retinal disparity. So let's break down that word there. Retinal, as in what your retinas see in your eye, and disparity is the difference. So the difference between what your retinas are seeing. So each of your eye detects its own image, that you get a different image in both eyes. But what your brain is doing is comparing those two images. And when there's a significant difference between what your left eye and what your right eye sees, it tells you that an object is closer up. So if you're able to hold your finger right in front of your eyes and do the left eye, right eye, right eye, Your left eye is seeing, for me, it's seeing the bottom of my finger, the bottom side of it. My right eye is seeing the other side. It can see my fingernail and the front of my finger. So my brain is saying, okay, these are pretty different images from what's being seen by my left retina and my right retina. So that's telling me that that object is closer to my face. But when it's farther away, when I do left eye, right eye, even when I'm looking with my left eye, I can still see both sides of my finger. So because there is not a big difference or disparity between what my retinas see, then that tells my brain that object is farther away. Our other phenomenon here is convergence. So convergence is when your eyeballs turn inward towards each other. So when your eyes look at something very close to you, they actually have to cross a little bit. So as an object moves closer and closer and closer to you, your brain detects how much your eyeballs are turning inward. And if it knows that your eyeballs had to turn inward more, then that object is closer to you. So it's detecting that little change in how much your eyeballs have moved. Both of those are going to help you to detect depth, but they require both eyes. Some optical illusions. So we've looked at detecting depth. So generally the Gestalt principles are going to help us to see things accurately, but sometimes things don't show up and that's accurately, and that's when we have an optical illusion. Perceptions based on inappropriate assumptions or discrepancies between visual stimuli and physical reality. This one here with the arrows is known as the Moeller-Lyer illusion. So in the top image, it appears that that middle arrow with the different ends to it is longer than the other two, but both of the bottom two are longer than the first one, when in reality the middle line of each of those is the same length. But it doesn't appear that way because of the surrounding arrowheads. That's the Moeller-Lyer illusion. The moon illusion, I don't actually have a description typed on here, but it's the idea that the moon appears much, much bigger when it's closer to the horizon than when it's higher up in the sky, it looks much smaller. And that's because when it's way up in the sky, we don't have an object to directly compare its size to. So the moon is obviously much, much bigger than the Capitol building. So because we have an object to compare it to, the moon appears bigger. Another famous illusion, this is called the Ames room. And these men are actually all three about the same height. But this guy looks significantly smaller than this guy. How is that possible? And the difference is that that room is not as it appears. It is not a normally shaped room. The room is actually trapezoidal in shape. The floor is not level, and the ceiling is also not level. And we'll talk about this one a little bit more in class. But the perception looks like these guys are just different heights, but it has to do with the shape of the room. Sometimes objects that can be represented two-dimensionally cannot actually exist in real life. If you take a look at this one closely, it looks like he's climbing up the ladder, but then he's also standing down the ladder. There's a famous artist, M.C. Escher, and we'll try to look at some of those illusions in class of things that work in images but not in reality. This is an example of bottom-up processing, and I've got some more about that here at the end of these notes. So some other things, perceptual constancies. So we tend to see familiar objects as having a standard shape, size, color, location, even when we know that other things in the picture have changed, like the angle, the perspective, or the lighting. So these are perceptual constancies. We also have shape constancies. We know that this door is still a rectangle, even though in this image, when it's opening, it changes its shape. Like it's actually more trapezoidal. Here, it's a total different shape, but we still perceive it as a door, as an object we know, because that's what our brain is used to. Brightness constancy is our brain is wanting to see these as the same color, whether it's dark or light. Same thing here, that these tiles are the same, even though over here they appear darker and over here they appear lighter. That's a color constancy. We actually talked about perceptual set already, but again, our perceptions can be influenced by those preconceived notions. If I say, think of Easter time, then letter A looks like a bunny. If I say, imagine going to a pond and feeding these, then you might see a duck. So whatever we change our perception of, we see something different. The last part here is about how we process perceptions, and there's two ways we can do that through bottom up processing and top down processing. Through bottom up processing, we tend to see the parts and then we see the whole. So, this would be like if you were listening to music, but you're able to hear individual notes in the music, that maybe you can pick out the bass guitar or you can pick out the melody. Or maybe if you were listening to a symphony and you can pick out the French horns apart from the whole group. Another way of looking at bottom up processing is when we're tasting things. When you're eating a food and you can detect just the pepper, like, oh, there's too much pepper in there. That's bottom up. You tasted a part of it instead of the whole. Whenever we go to a new place, we tend to look at like lots of little random things before we take the whole image of the place in. The opposite of that is top down processing. And here we see the whole before we see the parts. So perhaps we see someone in the distance and we're pretty sure we know who it is, but we fill in what we don't see. Better examples of this would be reading words automatically, that you just can't not read them. That is top down processing. We tend to see a group before we see the individuals. Some other examples in art here. Can you see a cat? There's not actually a cat there, it's just a bunch of dots and random lines, but your brain wants to form that whole image. This is part of Gestalt as well. Your ability to see that as a cat is top down processing. This is a pretty famous painting of people at the park. But if you look closely, they're really just a bunch of dots. But the fact that instead of you see people and pets and water and boats and all these other images instead of just dots, that's top down processing. Another example, it's easier to understand difficult handwriting when we try to look at whole sentences and whole words rather than just isolated words. I actually cannot read what is in this image. I just Googled difficult to read handwriting and that's what came up. But when we are trying to read difficult handwriting, it's much harder to read letters than it is to try to read the whole word. And then finally, another top-down processing example, and maybe you've seen some things like this that have shown up on different internet memes, where you can still read the whole sentence, even though the words are out of order. And that's because our brain is looking for the whole word. And that is also top-down processing.